Everybody, it's Mr. Allsup again, coming at you from my amazing home studio. Today we're going to have a really cool science lesson, but before we get started, some of you may be looking at me and noticing something a little bit different from the last few times I've been on here. You may look at my head and go, oh my gosh, he has no hair. And this is true. And it relates back to science. When we were talking about science before, we talked about how in science sometimes you make mistakes. And when you make mistakes, you have to fix those mistakes. You have to go through and you have to retry the experiment. Well, Mr. Alsop tried to cut his own hair. And when I cut my own hair, I cut it nicely, but there were some parts that were a little shorter than other parts. So I had to cut it again and try to get it all the same length. But there were still some parts that were shorter some other parts. So I cut it again to try to get it all the same length. But there were still some parts that were shorter than some other parts. And so after a few more tries, eventually my hair got to all the same length. Unfortunately, that length is really, really small. But sometimes this is what happens in science. Things that we think are mistakes end up being okay, because I think it looks okay with no hair. So whenever we do science, we always have to remember that it's okay to make mistakes, and we just keep going, and we keep trying, and we keep trying to see what we can do to maybe fix the mistakes that we made. And eventually, we hopefully get to the point where those mistakes are fixed. Now, today, I have a really cool lesson for you. I'm really excited about this. For some of you, you don't know this about Mr. Alsop. Mr. Alsop loves sports. I'm really excited about this. And so today's lesson is all about the Miami Heat. We're going to talk about the Miami Heat, and it's going to be amazing. And I'm so super excited to do this, and it's going to be really great. And I think you're going to really like it, and I think it's going to be really amazing. What? What? Oh, really? Not the Miami Heat. No? Oh. Well, what is it? Heat? Like, oh. Uh, okay. Not the Miami Heat. We're just talking about regular heat today. Like how heat is measured scientifically and stuff like that. But all my stuff is all right. I'm gonna need a different graphic. Can you guys get me something different? Just for heat. Really? That's what we got? Uh, I mean, I know we're PBS. We don't have a huge budget, but um, can we maybe try again? See, can we get better heat graphic? Maybe something looks like it's actually on fire. Ah, there we go. Okay, heat. We're going to talk about heat today. We're going to talk about heat and how it works and why it works and what happens and phase changes and all kinds of cool stuff. We're going to get to all of that stuff today. Our big question for the day is what really happens when I heat something up scientifically? And if we look at the bottom, that's the big long New York State learning standard that goes along with this, developing a model that predicts and describes changes in particle motion, temperature, and phase or state of a substance when thermal energy is added or removed. That's just a really complicated way of saying what happens when I heat things up and how could I show that with pictures or graphs or other things that would help us explain this. So when we look at this, we have to come up with a definition first. We have to come up with a definition for what heat actually is. So what really is heat? Because we talk about it a lot. We say, oh, turn up the heat. What we really mean is turn up the thermostat in our house. Or we say it's really hot out. Well, then we're talking about what is the temperature of the air. So that word heat gets used a lot for a lot of very different things. And some of those things that we use the word heat for are not really majorly the same as the definition of the word heat. So we're going to talk about how we define it in science. Now, when we define heat in science, we define heat as a measurement of the motion of the molecules or the atoms of a substance. Now, I'm going to talk a lot about molecules and atoms today. Just remember, atoms are the smallest part of everything. Molecules are constructed from atoms. So if I say molecules, you can include atoms because they're in the molecules. If I say atoms, you can include molecules because the atoms are inside of those molecules. Most of the time, I should be saying both of them at the same time, but every once in a while I might slip up and say one but not the other. You can always assume that when I say it, I mean molecules or atoms of a substance. So a substance is just anything. A substance is anything around you. All of the things around you, we can measure their heat by measuring the motion of their molecules, the motion of the atoms of that substance. So when you're not moving, or when the table is not moving, or when the chair is not moving, your atoms and your molecules are still moving. They're just moving at a scale that you can't see. So the chair's moving, your face is moving, even when it doesn't look like it's moving. The table in front of you is moving. The molecules in your jeans are moving. Everything is moving, even though you can't see them move. They're just moving at such a small level. They're just vibrating back and forth. They're not zipping across the room. That would be weird because then molecules from your genes would go shooting across the room, and we don't want that. These things move, but they only just vibrate just a little bit. They move in a very small pattern because they are solids. They are things that are closely packed together. They're molecules that aren't moving very much. Different molecules move at different speeds, and that's what heat measures. Heat measures how fast these molecules are moving. And based on their speed, it's also going to affect them in a bunch of different ways. So how fast is that motion happening? That controls something that we refer to as the phases of matter. You've probably all heard about solids and liquids and gases and how those different types of matter are out there. Solids are things like your table, like your chair, that don't move on their own very much, and they seem to be something that you can touch and feel and hold, and we'll talk a lot more about them as we go on. Liquids are things like your water and your soda and your orange juice and the milk you drank this morning. Those are liquids, and they have a very different construction. They're much more loosely packed together, and they're moving more than solids are. Gases, like the air around us or the helium in the balloons that you buy at the store, are moving even faster than that. And so they have an even looser structure. And so that speed helps to differentiate between those phases of matter. It helps to get us a difference between those phases of matter. Now you might ask, well, how does this happen? How is that speed changed? Like, how can I change the speed from one thing to another? And it all comes down to the fact that there are a lot of things that can speed up atoms and molecules. You may have seen fire. Fire is something that creates energy. It creates motion. It's a release of energy from an energy-containing compound. And the energy that it releases can be used to move the molecules of other compounds. So that can speed things up. Some of you may have had the experience of sitting in front of an open window with the sun coming in through the window. Sunlight coming through the window can take energy from the sun, contained in the photons in the sunlight, and can actually push that energy into you and cause the molecules of your body to start moving faster. And so your skin will start to get warmer and warmer and warmer the longer you sit in the window. Some of you may have also had access to a wonderful machine in your house called a microwave. Microwave oven, which is used in the kitchen to heat up food, actually bombards the food in the microwave with waves of energy that energize those atoms and those molecules in your food that cause them to start moving faster. And so that speeding up of your food is accomplished by the means of these microwaves. So there's a lot of different things that can do this, that can speed atoms and molecules up. Some of you have even found that you can probably do it by using something we call friction. If we move our hands back and forth next to each other and we let our hands rub up against each other, you'll notice that your hands get warmer and warmer and warmer and warmer. And that's because you're actually physically moving the atoms and the molecules in your hand. And so those are starting to speed up, and that's increasing the temperature of your hand. It's increasing the heat of your hand. So there's a lot of stuff that can speed up atoms and speed up molecules. Slow-moving atoms and molecules are referred to by the term solid. The atoms and molecules in solids are closely packed together, and they are not moving very much. They're tightly bound to each other. They're usually in a very solid structure. They don't move around each other very much, and they just kind of vibrate in place. And so these solids don't change their form very readily. They just kind of sit. So we can see things that are solids around us. Now, what happens when we start moving the atoms and molecules of a solid around? Well, when we start moving the atoms and molecules in a solid around, the molecules in it are going to spread out. Why does that happen? So, molecules are a lot like people. We use a way of talking about them where we talk about them like they were people. Now, imagine, if you will, a basketball court, like the one at the bottom of the screen over there. That basketball court has some areas on the court. If we look at the area right in the center of the court, that circle right there in the center of the court where they do the jump ball to start off the basketball game, imagine that circle. Kind of get it in your mind's eye. Now imagine you take 5 or 6 of your friends and you all stand in that little circle. Circle's not very big. 5 or 6 of you can probably fit in there, but it's going to be pretty tightly packed. You're going to be standing, probably touching each other's shoulders. You're going to be close. Now, in that circle, if I just tell you to just stand there and stay perfectly still, you can probably do that. You just stand there nice and perfectly still. Nobody moves. Everybody's still in the circle. Everything's going fine. Now, what if I told you that I wanted you to all just move a little bit? Not jumping around, not running from place to place, but just do a little bit of a move, just a little side to side kind of sway thing going on, just moving back and forth. And if I had you do that in that circle, you're going to notice that some of your friends might get their bodies a little bit outside of the circle, and then they'll come right back in. And then another one of your friends might get their body a little ways out of the circle, and then they'll come back in. You might see people just not able to stay so close together because I'm making you move a little bit. Now, what if I turned up the heat a little and I said, oh, I'm going to have you all dance while you're in the circle. I'm going to pick my favorite new TikTok dance, and I'm going to say, all right, we're going to teach you guys how to do this new TikTok dance, and you're going to try to dance in the circle. Now it's going to be really, really hard to stay in that circle. It's going to be horribly difficult because you're going to be dancing around and flailing your arms and moving your feet, and there's so much motion going on, it's going to be impossible for you to stay in that circle. And so some of you are going to fall out from the circle, and you're going to naturally want to be farther apart from each other. This is the same thing that happens to molecules in a solid when you make them move faster. If you heat up a solid and speed up the molecules that are moving in it, those molecules are going to start to spread apart more. They stop wanting to be so close, and they start moving farther and farther and farther away from each other until they get to a distance where they're not going to bump into each other anymore because of that motion that they're going through. And so when we see that, what we see is that the faster things move, the more it bumps into things around it, and the farther apart they get from each other. So more motion, more heat, more speed means more collisions, more bumping into things, means you want to get farther away so you don't bump into each other. And eventually, all of those bumping and all those collisions and all of that moving apart of stuff results in a change. That solid will change into a liquid. And you can see in the pictures, the molecules in those liquids are a little bit farther apart than they are in the solids. They're not quite so close together like they were in the solids. Now they're farther apart. When something changes from a solid to a liquid, we call that a phase change. And we even have a special name for it when something goes from solid to liquid. We call it melting. Okay, something is a solid, turns into a liquid, we can say that it has melted. And that is a phase change. It's a change in the phase of that object. And so all of that happens because of the motion of those molecules. How fast the molecules move determines what phase that particular object is going to be in. Now, some of you are probably asking, well, what happens when we heat up a liquid? Well, when we heat up a liquid, the same thing happens. Molecules start moving faster and faster and faster and faster, and eventually they get to the point where they're not held together as well, and they're much farther apart from each other. And when that happens, our liquid becomes a gas. And so you may have heard someone talking about boiling, where we take a liquid and we heat it up to the point where it starts to turn into a gas. So all of these are phase changes. Solid into liquid, liquid into gas. And they're all accomplished by adding more heat to whatever it is. And that heat is just more molecular motion. It's just more motion of the molecules in that substance. So as we go through these, there's another piece of this that starts to come in when we talk about how these different phases look. The first thing that we want to talk about is something called volume, and it's the like volume of an object thing, not the volume of like your headphone things. Volume is just how much space something takes up. So something that's a solid has what we call a definite volume. It has a volume, and that volume doesn't change. If I take a solid, like this gigantic 20-sided die, and I try to compress it and squeeze it and see if I can make it take up less space, I can't really make it take up any less space. It's still the same size as it was when I started. No matter how much I squeeze it, I can't make it take up less space. All right? It just doesn't work for a solid. Liquids are the same way. They have a definite volume. When you have a volume of a liquid, and the best way to actually do this involves using a syringe, which is something I don't have at my home, which is something that you would use to give someone a shot with, but you take the needle off of it. If you have a syringe like that and you put a liquid into it and you seal the end of the syringe and you try to push the plunger on that syringe to try to see if you can make that liquid into a smaller space, you find you can't. You can't change the volume of a liquid. You can't make it take up less space by squeezing it. However, gases you can. If you take a gas, like the air around us, and you put it into a syringe, and you seal the end of the syringe and you push on the plunger, you can actually decrease the volume of that gas. You can actually make it take up less space by squeezing it in tighter and closer together. So volume, how much space something takes up, solids have a definite volume, liquids have a definite volume, but gases do not have a definite volume, and that's what makes them different from each other. The other thing that we look at when we talk about phases of matter is the shape of that matter. Solids have a definite shape. This has a shape. Okay, it's a dodecahedron. It has a definite shape. That shape doesn't change. If I set it on the table, it doesn't change shape. If I throw it in the air, it doesn't change shape. Okay, it's always the same shape. Liquids, however, do not have a definite shape. If I were to take liquid from a glass and pour it into a bottle, it would take on the shape of the bottle. If I were to take liquid from the bottle and pour it onto the floor, it would take on the shape of the floor. It would have a very different shape. It would be flat, all right, as opposed to if it's in a glass, it's kind of tall. So those liquids don't have a definite shape. They take on whatever shape is around them. Gases, very similar. Gases do not have a definite shape. You can put a gas into any container and it takes on the shape of that container. So solids have a shape, liquids do not have a shape, and gases do not have a shape. At least not a shape that's definite. Okay? That means that it doesn't change. Liquids have a shape, but it can change. Gases have a shape, but it can change. But they don't have a definite shape, which is a shape that doesn't change. So that tells us a little bit about them. That tells us some of the properties of them. Now, the other thing we want to talk about are some of the ways that we can actually get heat to go from one place to another. So when we talked earlier, we talked about lots of different ways that we could create heat in an object. There are lots of ways for heat to get from one object to another object. The first way for heat to get from one object to another object is through something called conduction. And in conduction, the motion of one molecule is transferred directly to another molecule by the two of them touching each other. So if I have a molecule over here, and I have a molecule over here, and this molecule is moving really fast, and this molecule is not, and this fast molecule touches the molecule that's not moving very fast, it's going to start to make it move faster. That's conduction. That's motion being transferred directly from one molecule of a solid to another molecule of a solid. It's why if you grab a hold of a pan and the handle of the pan is directly attached to the pan, and the handle is made out of metal, and the pan is made out of metal, and you take that pan and you put it onto a stove, when you first put it on the stove, the handle is completely fine. You can touch the handle, you can hold on to the handle, it's not a problem, the handle is okay, because the stove is just heating up the bottom of the pan. But as time goes on, that heat is going to work its way up through the pan, and eventually it's going to work its way out into the handle, and eventually as it works its way out into the handle, it's going to burn your hand. So you have to be really careful with pans like that that are made out of metal and have metal handles, because sometimes those metal handles can burn you if they've been on the stove for a really long time. I think my favorite example of this is welding. For those of you who don't know, when you weld a metal, you heat a metal up so hot that the metal changes from being a solid to being a liquid. And when it does that, there is a lot of heat energy involved in heating that metal up to that point. That heat energy travels through the metal, which means that if you're holding on to it while you're welding it, you may not feel it at first, but eventually that welding is going to come up through the metal, through the metal, through the metal, and get to your hand. So you have to wear really thick, really protective gloves whenever you're welding to make sure that you don't burn your hands while you're trying to weld something. Conduction is really important for welders because it deals with how the heat travels through a material. Now there's another way that heat travels through a material, and this is called convection. Convection works in liquids and gases, and it results in hot things rising and cold things falling. So as you heat up things through that process, usually of conduction from below, it'll start to heat the liquid up, and then the liquid, the hot liquid, will rise. And as it rises, it will push colder liquid down. You've probably seen this in the kitchen if you've ever made macaroni and cheese. If you take the macaroni and you pour it into the boiling water, you've probably seen that the macaroni starts to roll around in the water. Some of the macaroni is rising up on the sides, some of the macaroni is falling down in the middle. And that's because of that convection current that's happening in the water. The water is rising, the hot water is rising, and the cold water at the top is falling. And so it creates this loop that happens with the little pieces of macaroni in your macaroni and cheese. So convection results in this kind of looping thing. When I was a kid, my parents heated our house with a wood stove that was in our basement. And so we had holes cut in the floors of our upstairs and covered with grates, obviously, so nobody fell into the basement. But we had holes in the floors of our upstairs so that the heat from the basement could rise up to the upstairs in the house. And then we left the staircases open down to the basement so that the cold air from upstairs in the house could fall down the staircases down to the basement to get heated up by the wood stove, and then the air would rise up and go up into the middle of the house. So it created this loop that happened with the heat in our house. The last way that we have energy moving from one place to another, heat energy moving from one place to another, is called radiation. And radiation is that motion, that heat energy, being transferred through a gas from one place directly to another. So there's no water involved, there's no solid involved, it's just a gas. And rather than doing the rising and falling, like the gases in my house that are being heated by the stove, this is more of what you feel when you sit right in front of the stove and you feel that heat coming right off of the stove and hitting right into your body. That's called radiation. That heat that's coming off of that stove, the way that it's moving is called radiation, and it's moving through the air to you from the stove directly through the air. So it doesn't have to go through any other system. You don't have to wait for it to rise and fall. It just comes directly to you through the air. Okay? So that tells us just a little bit about how heat works and what heat is. I really hope that we can take a look at now the question that we had, what happens when I heat something up? The simple answer to that question is when you heat something up, the molecules of that thing start to move more. And the models that describes those changes are those pictures that we saw of how the actual particles of that stuff are moving. So in a solid, they're not moving very much. In a liquid, they're moving a little bit. And in a gas, they're moving a lot more. In a solid, they're tightly packed together. They're close to each other. In a liquid, they're farther apart. And in a gas, they're even farther apart than that. So hopefully that's helped you to understand a little bit about heat. And hopefully I'll get a chance to talk to you all again next week. And I should have a little bit more hair.